位同学，大家好。那今天是一个很特别的，我们这清大物理系60周年的一个讲座演讲。那我这边呢很荣幸当那个介绍人啊，所以我稍微讲一下为什么我上台来介绍啊，因为我发现魔院长比我懂得更多啊，他其实这个方面他是专家啊，那个唐老师也是懂这个搭配之路。那我被指定叫上来是我的老师叫我上来的啊，所以今天这个讲座叫做Zhi-Xun Shen讲座，是我们施老师他的父亲以他父亲的名字的一个讲座，还有吴秀群老师的2个合起来的一个纪念讲座。那我被叫上的原因是因为我今天要介绍演讲的人是沈志勋教授啊，这个有一点点小渊源啊。那他们2位是在斯坦福大学都在 Bill Spicer 毕业的。那我相信那个施老师是师兄啊，所以那个是老师是师弟，
就只差1名。
对，所以按照这种小说里面来讲，一个就是我师父，一个是师叔，所以他叫我上来讲呢，我就2话不能说 no， 就说好，我上来讲啊。那但是我虽然是这个 Bill Spicer 这个第3代啊，但是我实际上那个生活从我当过主任，但是我研究没有做很多，做生活从啊。那因为那时候我跟这个施老师的时候，他已经做 STM， 所以我后来我是我们做 STM， 但是早期呢他有带我去布克做过实验，做同步辐射。那时候是 ITC 最红的时候，所以还是有看一些 paper 啊，看这个Superconductivity photoemission 的 paper。那当然这个名字出来，就是沈老师的名字就常在那个 paper 上面出来，所以就知道了。所以我对沈老师是有一点这个 background information 啊，他在这方面做得非常非常棒。那沈教授他是背景是他是复旦大学毕业的，然后他在这个大概大家很年轻，还有些人不知道，在大陆当初开始开放出留学的时候，第一批的学校卡斯比亚学生，卡斯比亚是10年嘛，每年8年100个人，就是全中国最厉害的年轻人送出来念物理，因为那时候其实没有什么管道可以出来。那这个推动的是李政先生啊，待会稍微讲一下，跟我们这边有一个关联啊。那所以沈教授是那时候出来的，就里面的精英选出来的。那在那8年里面，他又是在里面做的又是精英，所以精英中的精英做得非常非常好。那他最厉害的地方是做这个angle result photoemission， 用这个技术呢去研究了很多的新的材料系统，包括最有名是做强关联系统。就是他低位 Perry 1993年的 paper， 这是非常重要的工作。后面做了一系列的工作，不同的材料，然后但是他把这个技术用到了就是淋漓尽致啊。应该我想强关联系统做这个 photoemission 应该是第一把交椅啊。我这个应该他很确定不会这样承认，但我们自己看是这样认为了。所以我是觉得今天很荣幸他能来啊。那当然在沈教授在这个领域里面呢，他做得非常有名，所以我也不去念他得过什么奖。所以你可以看到什么 condensed matter 最重要的奖项，他全部都拿过了。他也是美国科学院士啊，所以他的成就是非常非常高。那今天他跟我们讲的题目呢，他也特别选的题目，他讲的是他的最爱的 topic 啊，所以我们这60周年这个喜庆呢，他还是给我们他这个最喜欢的研究 topic 讲给我们听，就是这30年来的进展。那他认为还有什么 hurdle to be overcome。我们一起欢迎沈志勋教授。
大家下午好，非常高兴有机会来这里跟大家做一个交流。当然刚刚也介绍了，就是也有很长的渊源，这个渊源就是跟我师兄在一起，跟我们的很多工作也跟清华的另外一位杰出的校友就是李东海，我们他的理论我们一起做过很多的工作，所以跟清华的渊源很深。我也想顺便介绍一下，就是我们那时候在 Spicer 读书的时候，我不知道大家是不是知道，就是 Spicer 是哥本哈根传到美国的第四代，所以我们算是 哥本哈根学派，就波尔的第5代、第6代的学生，是大家听说过这个 Slater determined， 这 Slater 是波尔的学生，就把这个带到美国去啊，在 MIT 就培养这第一批的学生，是这样，这是这个科学的传承。我这个题目是个强关联的题目。我今天早上在土木辐射也介绍了一下，就是当年我们在一起读书的时候，我们一起发表过一篇文章，就是氧化镍，就 nickel oxide 的一个 PIM， 你们还记得？这是电子强关联系统当中一个最著名的一个例子，就是单电子体系，就是 fail， 然后要一个多体的理由来解决的这样一个 nickel oxide， 在1985年那篇文章当中是说一个最经典的问题。我也想讲一下这个 context。我们在 Stanford 读书的时候，我们这个楼就叫 McCulloch Building， 这个楼是可以说是量子力学在工业界发展的一个最著名的一个楼之一。因为在这个楼的2楼里面，就是当年Bill Shockley创办了Shockley公司，然后Shockley公司倒闭以后，创办了贝尔强。贝尔强在孕育了像Intel，包括硅谷的100多家公司，都是这样的。所以这个楼里面，当然当初还有个教授在叫江默，江默有一个著名的台湾学生叫张忠谋，都是当初这个楼的历史，就说明了对科学的认识可以改变人类的生活。在40年代的时候，在贝尔实验室，那个时候量子力学已经从欧洲开始传到美国。他们觉得这个硅是能够 work 的，但我跟 Ken 做学生的时候，我们的如果主要是做半导体的表面的事情。任何接触过半导体的人知道，半导体的表面是个非常难的事情。所以这个三极管整整做了5年，就因为表面问题没有办法解决，所以这个三极管的 non-reciprocal 的这个 transport 就一直没有做到。后来还是 Shockley 非常 strong 的 personality， 又是 manager， 说如果这个量子力学是对的话，这一定是需要 work 的。后来 Bratton 终于把它做出来，这个属于一个1917年的这个工作。但是这3个非常接触。我刚才讲 Bratton 是做实验的 Shockley， 另外一个就是做理论的，这个就是江法利，是唯一一个物理学家得过2次诺贝尔奖，一个就是这个发明神经管改变了我的生活，另外一个就是我们今天讲的怎么样突破他在1972年做的法定库的虚分的这个理论，这是超导。也可以看出来为什么强关联和超导在物理学有这么重要的一个地位。基本上你可以说，物理学是有3个分支，一个用这个字叫大来描述，就是天体、星系这些；还有一个就是小来描述，就是最基本的物理学，基本粒子。我们这个领域就是多，怎么样把很多的东西放在一起，它可以展现无穷奇妙的现象，这就是多的现象的量子体系里的emerging property。所以我想，这个就是这样一个 context 来讲这个事情。 然后 sorry for those who had to don't necessarily speak Chinese, so I just talk a little bit about history and reminiscent of our time at Stanford we get in education. So I'll switch now and try to tell you a little bit about high-temperature superconductors. Intellectually, it's one of the great problems of our time because it was such a surprise. In other words, this subject, something we saw it should not happen, happened. It's like everyone. What I'm going to talk about is how we use electron spectroscopy to learn something about it. I'll break the topic down to things we know, things we sort of know, and things a little bit more speculative, so in this sequence. That's why I said, when you hear a talk by ITC, okay, you often say, how come those guys been working on it for 30-some years? They still haven't solved. And I hope it is not true. We made tremendous progress. On the other hand, it's also a tremendously hard problem. The intellectual questions being raised, profound. The phenomenon you see is fascinating. So that's what I'm hoping to accomplish. That's why I said, let's see. Yeah. Okay, strides made and hurdles remain. I'll talk about the progress made, then also the hurdles. I have the fortune to collaborate over that. I'm going to talk about the summary of work being done over the last 3 decades. So this is the team we work very closely, and on this project, I particularly would like to acknowledge the contribution of Dong Hui-Lu, Marco Professional. Of course, we collaborate a lot with Zhi-Xun Shen. I understand that Zhi-Xun is also spending time here. So it's really a collaboration funded by the Department of Energy. We have the fortune to work with a fantastic materials group who provide us with excellent samples, both at Stanford and also outside Stanford. Then I really benefit tremendously working with Siri, who's below. As I said earlier, is just a brilliant physicist to interact with. Okay, this is the Cuprates superconductivity. It was such a surprise that we saw this a sort of weirdness. Sometimes you're tremendously influenced by your success. BCS was so successful, we saw this 30 Kelvin was about the limit. When we were students, since we talk about time of our students, there's really very little hope. This thing will go further up. Then something unexpected happened, and Mueller and Benrose. I spent 1 year on sabbatical in Zurich, spent time with Alex Mueller, and he always said, yes, one of the luckiest thing I have was I didn't know superconductivity. I didn't know you have to look for superconductors starting with good metal. Okay? You start out with good metal looking for better superconductor. He said, I didn't know that, so I started with the insulator that I find the Cuprates. But as you see, he works on intuition, just like our advisor Bill Spicer when he developed formulation. Also in some experimentalists, you find that intuition is the most important thing. instinct, and others have that. It's also interesting, recently, as you know, that hydrogen superconductivity discovered in the nickel compound. Okay. But when you read his Nobel lecture, he actually started in 1983, the famous paper of 86. Okay. 83. He actually started with the nickel. Okay. And they didn't make the nickel to work, then they switched to copper and make it work. Okay. So it's quite interesting. Now we come back, there's another family of hydrogen superconductors. Now, we can ask, maybe I can elaborate. His idea comes from Zhi-Xun Shen. They were working on ferroelectricity, quantum ferroelectricity, Zhi-Xun Shen. His idea was that it's an oxide, so the screening is extremely poor. Okay. Therefore, if you have a very poor screening, then you could have very strong electron phonon coupling. In particular, he thinks the octahedral has this breathing Young-Taylor distortion. That was the reason he said it could be hydrogen superconductivity, and indeed that was successful. And it's significant. You see, the Nobel Prize Committee usually is extremely conservative. Okay? They wait 30 years, okay, or longer. Most of the time. But the superconductivity is a very rare case. It was discovered in 1986. The Nobel Prize was given in 1987. Okay. Also give you a sense of how the community thinks about it. Now, so his idea is that this poorly screened system should have very strong electron phonon coupling that gives rise to superconductivity. Then you get a problem. This problem was articulated extremely well by the great physicist Bert Matthias. Anyone who worked on superconductivity, you must have heard about the Matthias rule. Right? And until ITC, Matthias energy ball holds the record for high temperature superconductivity in our team. He said, you look for back superconductors right before they go to hell. Okay? What that means is that he said you turn on the electron phonon coupling to be stronger, stronger, stronger. Good for you. Okay? But when the things become so strong, the material becomes unstable. So there's a structural instability, it becomes a different material. This morning I talked about it. If you pump the system so hard, you really are studying different material. Right? So that's the basic idea. This is the source of the reason back then. It's saying that 30K is the highest limit. So Mueller's intuition was immediately collided with this thing by Matthias. Okay. How are you going to avoid structural instability by you can turn on the intelligence as strong as you want, but you're going to create another instability. Competing state, as you already learned, is always a problem for you. So that's that. So this immediately lead to another proposal. In 1987, Phil Anderson said, aha, okay, the Cuprate problem is an extension of the great problem of transition metal oxide, the great insulating problem. As I said earlier, nickel oxide is a classical case of an insulator. So Anderson then said, no, this idea of electron phonon interaction maybe accidentally leads to the discovery of the physics is really a result of the same as the insulating problem. Okay. And the physics of high temperature superconductivity live in the two-dimensional Hubble world. Okay. The same physics give you the insulating state is the physics give you high temperature superconductivity. And you can see in the ensuing time, then the high temperature superconductivity research sort of bifurcated into two fields. Okay, that's high temperature superconductivity research in real materials and high temperature superconductivity research in Hubble world. Okay, there's numerical simulation, quantum simulation, there's a lot of stuff going on. This also symbolizes why it is hard. Remember, Hubble model is the simplest extension of the single particle approximation, on-site interaction. By just adding that, we already have very hard problem. I think the exact diagonalization of the Hubble model still is a very few atoms, right? 30-some atoms. Now, of course, the MRG making more and more, we learn more and more about the Hubble model for this. So that's the context. Okay, you have an idea, you find something remarkable, then people say, oh, you just are lucky, accidentally, with a wrong idea, find the correct thing. Okay. Then there's a proposal saying, hey, this have nothing to do with the original idea. Okay. I hope now, with 30 years later, you will find actually both Mueller and Anderson have a lot of, they have grasped a lot of the correct physics. Together, their ideas find a very interesting way to answer this great problem by materials. How are you going to have a strong coupling without structural instability? Okay, so that's how we're going to have the lunch and still having it. So technically, here, what I'm going to talk about, I'll talk about the progress made, puzzles remain, and I'll talk about the essential microscopic ingredient. Then I talk about, because of intellectual importance, talk about how to benchmark the Hubble model. I would say this is extremely solid. And the puzzle, of course, is an open question. Here, I would say we know what's the answer to this, but this is a more speculative question. So that's what it is. Okay. The Cuprates is a two-dimensional system, and it has this magnetic insulator we call a Mach insulator. You dope this, you create this beautiful superconductor. Okay, and that's the nice thing about this is that if you're studying material, as we study more and more different materials, Cuprates have two things. Simultaneously, extremely simple, single band, but also tremendously rich with all the interesting. That's the richest about the many body physics in this system. This is the simple aspect. You can see the band structure, you see the Fermi surface. It's really very, very simple. Okay, but it's simultaneously so remarkable. Okay, and the technique I'm talking about is called angular formation, based on the photoelectric effect of Einstein. And you have photon coming in, and you eject the electrons, then the electrons going through an energy filter and being detected. Okay. I went into more detail about why this technique become a dominating technique, just because of the quantum efficiency of photoelectric effect, as well as the fact that these hemisphere just extraordinarily good imaging device. You know, sphere is a very good imaging device. Therefore, anything you measure at a detector, you can trace back. Okay. Therefore, you can do multiplexing, and you don't have to have a contact. You can manipulate the charged particle by electrical field. All those are efficiency in this. However, if you are interested in many-body physics, then what you really are measuring is the occupied state and then the band dispersion. If you ignore all the interactions, you should have seen the energy momentum relationship of a state is the delta functions each of them. Okay. Now, if you are interested in many-body physics, then it's the translation of this delta function into this compressed shape. Okay, then that's by analyzing the compressed shape, then we learn physics. This was the paper I wrote with Andrea Damascelli when he was doing postdoc at Stanford. So we all know the Cuprates are unconventional superconductors. So then you can ask the question, what do you mean? What is an unconventional superconductor? There are many ways you can define them. One would be the sign change, the order parameters, such as non-test wave. Okay? Then all Cooper pair are not spin single, or it doesn't have the zero center of mass momentum. Or there's a disconnect between temperature of pairing and real global phase flow. All those can be defined as unconventional superconductor. If you define it this way, then there are many unconventional superconductors. I indeed the Cuprates break several of this. Okay. So that's what I want to talk to. Okay. I would say Cuprate, I feel is pretty solid. Now to say that it had a D-wave pairing. Once you know it had a D-wave pairing, you immediately know the answer to this one. Its Cooper pair must be spin single. If the performance, if the orbital is even, then the spin has to be odd. Okay. And to the extent we know it's a zero center of mass. However, there's another thing about Cuprate which is very unusual, is the disconnect between pairing temperature and TC. These are the two things I'm going to show you with formation. This is the earlier work about the Cuprates and begin to indicate that it looks like a D-wave between angle without measuring at the 45 degree. If that is a D-wave, and in this case, the order parameter changing sign from positive to negative, then they have to go through zero. And that in the amplitude, that's today it's a trivial, but 30-some years ago it was a tremendous experiment. It was strongly fought by people, I think, back then. Because the conventional wisdom was it was an S-wave superconductor that mostly coming from the penetration gas experiment, looks like it's basically activated behavior. Of course, as time progresses, we all know this experiment, together with the microwave penetration gas experiment, force a delay. And of course, there's many groups and many techniques, in particular the phase-sensitive experiment. We have, but from the formation point of view, then you can see the work here that you can now measure the spectrum around the entire 3D surface. You can see it shifts. Just plotting the energy position of the shift as functional angle, you see the data points, and the blue is the Zhi-Xun Shen. Okay, it's get to be pretty good fit to this. Now, if you go a step further and ask yourself, so we have a D-wave pairing, okay? But is the pairing determine the TC? Okay. For a D-wave superconductor, the most sensitive measure of the superconducting gap is the gap near the node. This is particularly true in Cuprates because, remember I said earlier, there's other instabilities competing with superconductivity. And that could also create a gap. Okay? But we know the node is the superconducting gap. Okay? Here in this work, when in research we still do thesis, what we find is that the slope of the node is the best measured by the slope. And for those 4 samples of TC from 40 Kelvin to 90 Kelvin, you see the slope essentially doesn't change in this range. Okay? Certainly, there's no factor of 2 change here. So this telling you that the change of TC from here to here is not related with the change of pairing. Of course, as you go to different part of doping, then becomes what you would have expected. As TC goes down, the D-wave node gap goes down. Okay. So what is going on? I just said you didn't see something you expected. It's scaling between the gap and TC. But here, it's getting even worse. You actually see something you shouldn't see. And that's when Donald Fan was doing his PhD with me. What we plot is the strength of the quasi-particle peak as a function of doping. You see sort of it correlates with TC and turn around at 19%. Remember that year 2000, okay, the quantum critical point at 19% was not very clear 25 years ago. But the data already suggests something here. But more importantly, you see, what we are measuring is so-called single particle Green's function. You take electron out and measure the spectral function. We should not have the result sensitive to basically superfluid density, which is 2-particle correlation function. But nevertheless, empirically, this result correlates with superfluid density extremely well. Okay. So that is another term. To tell you again, this TC is not connected with the parity. Okay. The third one, of course, is so-called the pseudo gap or the normal state gap. In particular, this suggested is the appearing above TC. And here I'm taking the spectrum at the antinode as a function of temperature. This is symmetrized spectrum. As you increase the temperature, by the time you reach TC, the gap doesn't close. It closes at a temperature much higher than TC than the expander. So, but if you looked at this and you said, this temperature evolution of this gap is so smoothly across TC, it may as well be the same. Okay. So this will say, hey, looks like there are some pairing above TC. Okay. Now, another thing that if you look at the D-wave node, that's where the gap maximum is. If the Cooper pair strength is a measure of TC, okay, then the size of the gap and TC should be correlated. Okay. Again, as you go to underdoped regime, the gap gets bigger, even though the TC gets lower. again, it's saying that, hey, there's no connection between TC and the pairing gap in this sort of vast regime of doping. Okay.
A question.
Yes, please.
Is the evidence so far strong enough to rule out DCS or electrochromic interaction in general?
No. In fact, I will come back to this, if you're okay. Yeah. I think there are deficiencies, but it's still the framework of pairing is sort of more or less within the framework of DCS. Right? The Cooper instability is still a DCS. In fact, I would say it's much closer to the DCS regime than to the resonating valence spark regime. Okay. Because Cooper pair, as I showed you when I see the DOA gap, the gap occurred around the underlying Fermi surface. But when you have a Fermi surface, that means it's a momentum space description closer to the truth.
So did people observe isotope effect in this system?
That's far more compressed with compound. You see, isotope effect typically a percent or 2. Okay. We have understood the physics of 100%, factor 2 different. So small 1% effect is way within the noise. Other uncertain, other puzzles. So this will hint to say, hey, there got to be some pairing about TC. Then you can ask yourself, here I'm showing you the doping, for example, with doping in the overdoped regime. I hope you can see, as I go from going from high temperature, going down to lower and lower temperature, you see a peak, the dashed line is the chemical potential. By the time you reach to about 130 Kelvin, the single peak, I hope you'll see, begin to split into 2, and eventually one of them become the superconducting coherence peak. Okay? This single particle peak split into 2 is exactly the behavior of a pairing when you have a single particle break into 2 Bogoliubov quantum particles, right? With the coherence factor U squared and V squared, each equal to half. So now, should that be the case, then you say the gap in the normal state above TC needs to be particle-hole symmetric. That's a hallmark of superconductivity. You can also have a gap due to other instabilities, but it will not be particle-hole symmetric over the entire momentum space. And that needs to be checked. Okay? For example, here superconductivity happens as a particle-hole symmetric, but the charge density wave will not be over the entire momentum space. And we did that testing. And we measured, you can still see the gap at 85 Kelvin, above TC, and we can measure the entire momentum space. And you can see that there's an upper branch of Bogoliubov particle and the lower branch of Bogoliubov particle. They're just everywhere symmetric around the center. Okay, so it's a particle hole symmetric, consistent with what you would expect. Okay, so let me stop here to say, in the conventional framework, anytime you see a gap, it's a pairing should only happen in the superconducting state of DCS. But we have reason to believe pairing above TC. Okay. So to see a gap in the normal state above TC, often in the literature, it's called a supergap. But what I want to say to you is that, in fact, if the experiment gets better, there are more than one gap in the normal state. One of these two, which are being focused on, is the gap due to preformed pairing above TC. But now I'm going to show you evidence of the second gap, which is related to the higher energy scale, which is the residual of the Mach insulator. Okay. So far I'm telling you a gap in an overdose regime. Okay. Now, showing you data. It's relatively narrow, 5% doping range. Okay. Here's the 19%, that's it. Now, if you are below the 19% doping, you see a spectrum look like this, okay? Different doping. In a nutshell, you can see as I go to lower and lower temperature, I hope you will be convinced that the dashed line is the chemical potential. But at lower and lower temperature, you see it even well above TC, you see a suppression of density state near the chemical potential. Okay. Remember, we are measuring at high temperature. Okay. That means at a finite temperature, you can see things above the Fermi level because they are thermally populated. Okay. So that's that. Okay. Now I hope you will see the gap had the energy scale is much larger than the superconducting gap, it's about 100 million. It's very poorly defined gap. Okay. Now look on this side. Okay. You notice that there's nothing happened at the dashed line. Okay. Until it gets to a point that one peak split into two peaks. You can see, I can say that red is just one group of spectra, the black is another group of spectra. Just across this boundary from 18.5 to 19.5, it is qualitatively different. Okay, the data. However, if you cool further down below TC, okay, those spectra, you can see on this side, I already told you, this single peak now split into two, and just as if pairing already happened here. But on this side, I hope you'll be seeing the development of a shoulder here, and eventually this shoulder developing into the superconducting peak. Okay. One thing you can see, if I show you data at a high temperature, as a function of doping, you'll see on this side and this side are very different. Okay? But if you only take the low temperature data, you find the difference is much more subtle. Okay? In this sense, I mean, if you quantitatively analyze it, they're still different, but it's much more subtle. Okay? So the thermal effect is clearly. Therefore, we can say that here the phase diagram, there is an energy gap across the entire doping range, which is somewhere around 50% above TC, 30, 40, 50% above TC. And in overdoping regime, we've tested very carefully, and it's part of symmetric. And this gap, what I call preformed pair. Okay. Then in underdoping regime, there is a higher energy scale gap, and this is a gap I would call something a soft pseudo gap, and this, by virtue of energy scale, we think that's related to the instability coming from the fact it's a doped magnetic insulator of that scale. Okay. Now, if you say, okay, if this is the pairing temperature, then what is the spectroscopy evidence of this true global phase coherence, which we know is thermodynamically required? Okay. You know, for superconductivity within the VCS frame, well, there's actually 4 things need to be true, right? The first 2 we always familiar with, zero resistance and Meissner effect. However, you need to have a singularity in the specific heat. It's the second one, phase transition. And also in VCS, there's an energy gap turn on at DC. In the Cuprate case, this happened in 1986, and this happened somewhere around the 89, 90. So they are all 25, 30 years ago. But the spectroscopy part remains a puzzle. We saw it's the gap measured. Now we are sure that gap indeed is superconductivity, but does not tell you the global TC. And the question, what is the physical and quantity have a singular behavior at TC? What you can now do is make a really very precise measurement as a function of temperature. And for anyone who has certain experience with formation, okay, and for this matter, STM, what we can do, the temperature-dependent measurement is extremely delicate if you want high precision. It's just very hard. So in many ways, the important part of this 20,000 Nature paper is the supplement. We can show we start out with this spectra at a low temperature. We do this cycling of temperature, and we go back to the original temperature and show the spectra after the entire thermal cycle were identical. It's extremely important, otherwise you're not going to get it. Then we now have the data, then we can ask ourselves, okay, instead of denser state, because we have many body interaction, we don't have a single particle denser state. What if I just use the spectral weight at 0 energy as a spectator of denser states? Once I have a spectator of denser states, then I can calculate the entropy. Right? It's a simple function, just Ashikoff and Berman, and you have density. If you do that, you can get an entropy like this. And if you now do a derivative of that entropy, you see a singularity at the correct TC. Okay? So now we can say how we actually can use the formation to get this image. We know the spectral wave at the 0 frequency that gives you the singularity. The singularity there gives you the phase transition. Then you say, boy, this is a very expensive way to measure specific heat, right?
So is the data consistent, exactly the same consistency?
Yeah. Yes, yes. The solid line is the specific heat measurement, the dot is the formation. The answer is yes, it's expensive, but we also measure tremendously inside. Because once you know that, what a formation can give you is the angular dependence. Okay? You can see that at the end-node, the singularity is big. As you go towards the node, the singularity gets smaller and smaller, eventually not. Okay. That's exactly what you would have expected with phase fluctuation model in a dual superconductor. So we now know we have a normal state pairing. The TC was determined by phase fluctuations in that system. Okay. Okay, I hope to have shown you D-wave pairing and also the disconnect DC. There's a pairing in the normal state, and the phase fluctuation is why global superconductivity happens at a lower temperature. Those are the things we feel we have enough results to be confident about. The next question is, what about other things? You know, if you really look at this, one of those phase diagrams, many things happen. You'll be depressed because it's so complicated. But it is core to this to think about is something called the pseudo gap. And it's also think about the puzzles remain, right? If we understand this phase, we would not have called it strange matter. The fact that it's strange means it's not something we fully understand. And pseudo gap is the same way. It's just a way to think about it. So those are the things that puzzles remain. But I'm going to tell you what the likely ingredients that could have covered our phenomenology. To the zeroth order, the pseudo gap really is a phenomenon to say that the Fermi surface sort of stopped in the middle of nowhere. Remember, Fermi surface is a geometrical concept. It should not stop in the middle of nowhere. So that is something, and you can see here, this is the situation. You can see, this is a very generic Fermi surface happening in the middle of nowhere. Okay? So, in the most of the Cuprates superconductors, its so-called core node carrier are positive. So in this case, the pseudo gap happened near the ground zone boundary. Okay. Under these circumstances, it is difficult to know what is the microscopics because too many things happen at the ground zone boundary. There are Van Hoff singularities, there's a collective mode coupling, and these boundaries also happen to be this Fermi surface across the underlying antiferromagnetic zone boundary. So it is difficult. But on the other hand, the electron-doped system, okay, it turned out to be a very good way to gain some insight. And you have this so-called hotspot phenomenon. The red, this is the underlying Fermi surface. You notice that the spectral intensity is being suppressed when this underlying Fermi surface and the antiferromagnetic zone boundary crosses. This we call the hotspot. Okay? And of course, the magnetic scattering in this case could give you something reminiscent of the pseudo gap. So we will say at least the antiferromagnetism is a component of the pseudo gap phenomenon. Okay. But more recently, we were able to work with Donghai and Zhi-Xun Shen based on the more data to show actually the physics is richer than that. Indeed, you see the spectra being suppressed at a so-called hotspot in the antiferromagnetic zone boundary. But the spectra show two components. There is this bigger gap here as shown between here and the Fermi level. Then there's also a coherent state near the Fermi level here. Inside the magnetic gap. Okay. For all of us working on insulators, seeing a gap, seeing states inside the gap is no big deal. There are many impurities can give you the state in the gap. What is the big deal is that These state later on, as you go below TC, turn into the coherent superconducting peak and show the momentum dependence. So that is the important one. And with Dong Hai's work, it turns out you have to consider both the anti-ferromagnetic amplitude of the magnetic order as well as the orientational fluctuation. And that orientational fluctuation can give you this physics. Just like a superconductor, you have the pairing amplitude and you also have the phase fluctuation. Okay? Okay. Now, this, of course, tells you something about, we have D-wave pairing, which is unconventional. Okay. Now we have evidence to believe the anti-ferromagnetism did quite a bit on the electronic structure. It's telling you this physics of magnetism of J is very important. Okay. So that is naturally leads to this kind of physics of the Hubble model. Okay. So leads to what I said earlier, is the high temperature superconductivity in Cuprates equivalent to the physics of the Hubble model. Now, so what we want to answer will be, is the Hubble model both necessary, we think, pretty sure about that. Is it sufficient? In particular, is it sufficient to describe the interaction of two doped poles into the system? And that's where we can benchmark. I want to first show the role of the anti-ferromagnetism. You can see that here is the band structure calculation. Here is the dispersion seen in the data. It's pretty clear that there's not very good agreement to data in the series. Okay. And most importantly, you see the data show a maximum at halfway, between half-pi rather than pi. And that, of course, is a clear indication that the magnetism is important. And this some of the early work, collaboration with Bob Bergeron's group, when he was still at MIT, and and you can clearly see that if you consider the spin exchange, then you can get a pretty good agreement in the sense that the theory will predict the amount of dispersion is completely controlled by the magnetic interaction J. And J can be measured by the neutron data, and you can see a very good agreement along certain direction. But on the other hand, if you go to the zone boundary, you can see even the magnetic model has a pretty poor agreement. Okay? And that, remember, is where much of the zodiac physics happen. So we went out and tried to say, can we test the Hubble model? The trouble is the following. You know, even though the Hubble model is very simple, but to this day, there's no reliable calculation of the Hubble model in 2 dimensions. In those circumstances, when you have a disagreement between theory and experiment, you don't know whether it's the model is incorrect or whether it's the calculation of the model is incorrect. So we say the better way to test is in a one-dimensional system. In one dimension, we at least have the beta ansatz, and we know the solution of the Hubble model. If the model is correct, we know the answer. That's what we set out to do. And so we try. As you know, in one dimension, there is this famous phenomenon called spin charge separation. And that's to say that the original single band now split into spin-on and hold-on. This is really B.J. King and Chen King's work. And you can see that describe physics very well. Okay. This is the case. The electrons split into, this the spin arm and this the whole arm, like carry the whole and spin them. This case is to say that, hey, your J is very important. The Hubble model is necessary. But what we want to know is, if you dope two holes, what about the interaction between the two holes? This experiment was done in an insulator. Effectively, you dope the system by formation process. You take out one electron, you dope in the hole, and we study the dynamics. And we have tried to grow single crystals of this one-dimensional system, but you just cannot dope them. They always stay separate. And until the oxide MBE was the system developed. In this case, I think we were able to grow MBE films. You can see here there are two domains, 90-degree rotated, so you can see two sets of one-dimensional film surface. And we can dope the system up to 40%. Now with that, then we can compare with series magnetic profile.
So, so when you say it's 1D, you mean the 1D is at the grain bound?
No,
Is that,
it's one-dimensional crystal.
it is one-dimensional
Yeah,
crystal?
it's
So,
basically copy. It's a chain compound.
oh, it's, okay.
Okay. So now we can compare. This is the data, and this is the Hubble model. I want to bring attention to this dashed line. That is a point in momentum space called 3kF. We know that that intensity is a strong measure of the interaction between two carriers. With the lover's eye, you may say maybe there's a tiny bit. That's the Hubble model. This is the attraction of two carriers in the Hubble, self-generated by the superexchange interaction. So if that doesn't work, then we say, okay, that's the Hubble model, let's add one more term. And we can add one more term of next neighbor interaction. And if we add a positive term, it doesn't do much. But if we add a negative term, then you can see the reason experiment. In other words, in the real material, there is a next neighbor attractive interaction not captured by the Hubble model itself. And the nice thing about this is that just by adding that one thing, just adding one parameter, you can describe the entire doping dependence. You can see that as you increase the doping, they shoulder disappeared. Okay. So, I hope to tell you that somehow in the real material, there is next neighbor attractive interaction which is not captured at a single band Hubble model. So you need to supplement it. Then the question will be, what is the microscopic source of that model? Okay. And then you basically, there are very few things that can give you attractive interaction. One of them is the electron phonon interaction. Okay. And you can clearly see that basically, when you have electrons coupled to a phonons, you see a sudden change in electrons velocity at the phonon frequency. Remember that the slope is the velocity of electrons, and you can see a sudden change of slope. So this we've done. So there are pretty strong electron phonon interaction in this system. I should also say this is more technical, but this is the thesis work of Zhi-Xun Shen, and he was able to explain the line shape. Remember I said the total dispersion described by magnetic interaction, but you cannot describe its tremendous width, especially the width at the top of the feature, you can see here. This width looks like a Gaussian. Okay, so you need something else to further broaden it, and that he termed as the prolonged phenomenon. By resolving that, we will also explain the long-term question about what happened to the chemical potential when you dope the system. Okay. This was pointed out by Jim Allen that there's inconsistency among the doping you have and expected chemical potential shift. Okay. So we were able to do that. So if I will now put this together, then we can say that there's a strong spin interaction and there's also lattice effect. But usually, electron phonon is bad for D-wave superconductor, right? Because they're pair breaking of that. Unless you have a situation the momentum transfer is small. Okay. And it's actually on the forward scattering of that. So these two could happen. Then also, of course, there's an interesting question. Is the D-waveness and the highness of TC the same question? Okay. So you talk about the isotope effect. Also, what I would say that there are puzzles much bigger than the isotope effect. Until that puzzle is being solved, it's not very meaningful to talk about small effect. Okay. So, what are the evidence of small Q phonon? For example, this will be one thing. We know that the disco is coupling to this D-wave-like phonon, the P1G. That's the work of Tom Devereux and really the thesis work of Tom Chu and the Shiva at Stanford. And we can really explain the momentum dependence of that. And this one is very good for D-wave superconductor. Okay, so it can enhance. So you say, okay, fine, they are there. There's a distinction between they are there or are they relevant? Okay. So the next question is, this is the thesis work of He. Now he's a professor at Yale. And it as a function of doping in this one. And you can see in this narrow doping range, I'm measuring here red data points, this gap of superconductivity. In this doping range of 4% change, the gap has gone from 10 millivolt to 40 millivolt. It's a factor of 4, 400% change in a narrow doping range. Okay. In this regime, 2 delta over KTC is what you expected for D-wave DCS. Okay. But here is different. So then what happens? Also in this regime, this feature, which I said earlier, the electron phonon feature, really increases with this. There's a strong correlation between electron. At the same time, you know, the electron phonon interaction in a typical matter should not change a lot in a small amount of doping. So the additional physics drives that. So what we believe that the system just forms an ecosystem, sort of feedback loop, and all those interactions is on top of each other. So as I go from higher doping on this, I see I'm going from a weak BCS superconductor to a much stronger, but also much more complex superconductor by boosting by these phonons. The 2 delta over KTC in this range is approximately 10 to 12. It's a very large number. Okay. We're also influenced by, here's another example in a different superconductor. So if you take an electronic pairing and add up with the interface phonon, we know that you can end up with the high TC. Okay, that's again this is the idea from Donna. Okay. So I hope to have sort of convince you that since we are confident about D-wave pairing, the unconventional disconnect TTC pairing, okay, we think the central puzzle remains the pseudo gap. We think both magnetism and electron phonon interaction is essential ingredient for this. Now, finally, is the key question. How are you going to end up having a high TC, but without any other instability? Okay. How this? It turns out that you could have electronic correlation, amplify the electron phonon coupling very strongly. So the electrons will see tremendous influence of the phonons. On the other hand, the phonons would not see tremendous effect of the electrons. Okay. And this way, you could have the electrons experience strong interaction without the structural instability. By combining those ideas, you may well be able to answer this question. For aficionados, this effect was pointed out by both Mishchenko and Nagaosa, also Ulla Gunnarsson. Okay. This, in a very simple way to think about it, in the Cuprates problem, when you have a doping mark incident, there's something called a doping X, and the Fermi surface 1 minus X. Let's say if X is 0.1, so there's a 0.1 and 0.9 difference. Because you reduce the number of carriers, you reduce the impact of the electron on the lattice, but the electron on the other hand still receive the full blown phonon interaction. And you'll see they all happen in this regime. Yeah. So, and let me just end by this. I was giving a talk, so I was just saying this might be the possible answer to this. I was giving a talk, and then my colleague, Bob Laughlin, and those people who don't know, he won the Nobel Prize for giving the fraction on the home. So he was just sitting there, I saw him taking notes. Instead, he sent me, and he said, oh, here's a gift for you. And that's his cartoon of summarizing the talk. He said, really, you just talk about this, the phonon effect, the phonons being amplified by the Mach effect. That's the possibility. Tremendous insight and great artist. So I hope the question will be, is that true you can amplify the electron correlation can amplify the electron phonon interaction by order of magnitude? And I discussed this in more detail this morning in time without full emission. And indeed, we can show here is the results of that dynamic mean field. This is electron phonon interaction. The density functional theory, if you include the Coulomb interaction in the dynamic field, there's almost order of magnitude. Now the experiment is good enough to have the error bar to show this is the correct answer. Okay? Okay. So, I hope we come back to the full circle that the fact now we have other families of superconductivity. Now it's about also 90 Kelvin in the order of magnitude. Make you want to take a step back to say this is more general phenomenon rather than a very fine-tuned specific model. Although Anderson's idea had embodied tremendous thing, but the nature, it turns out, had a way to combine the two schools of thought of giants, Mueller and Anderson, in a way with human collaborators to answer this question, how you can have the cake and still eat it. And that's the dilemma of high temperature superconductivity. So I'll stop here and happy to answer any questions. Thank you very much.
This is Shen. Thank you for the great talk. I have a simple naive question regarding the two gaps in the pseudo gap phase you mentioned. The higher temperature gap, you said this is related to the Moore physics, anti-ferromagnetic Moore insulating. Say, what are the experimental signatures of the link between the second higher temperature gap and Moore physics?
It's a great question. I didn't have time to elaborate. When I was talking about this work from the single hole case, I said at the part of the zone phase, that's the energy scale. Still the TJ model doesn't quite work. And if you look at the energy scale of that problem, that phenomenology looks like the pseudo gap seen in underload energy. That's the reason.
You seem to continue to rule out the possibility of the density wave. Is that?
It could have a situation, it happened, but I don't think it's sort of the main physics behind. I would say the beauty about the Cuprates is the physics so rich, many things happen, but not all of them are adding on top of each other. In other words, they may not have the causal relationship between the highness of TC. My own thinking, I think everyone in this field is, because the problem is so fascinating, rich, and even with the deep. Everybody's thinking evolves. I used to think that D-waveness and highness of TC are the same thing. But what I think, they may not have to be the same. Yeah. It could be that this is one of those situations. Several factors just happen to be the star aligned. That's why they gave you extreme property. Yes.
Thank you for the talk. We discussed several times that there are many mechanisms that open the gap at the front end.
Yeah.
So they shift around kinetic energy. That's a question regarding the condensation energy. When you combine Mott and phonon mechanisms, where's the energy really lower at the end? Because a weak isotope effect probably would mean it's not ending up at the phonon. So it's actually the magnetism maybe, or the neutron.
That's a great insight. Thank you very much for the question. Mike Norman and others have proposed many things about condensation energy. The reason I'm hesitating to this is the physics of competing order. So many things happened, I can only pick one set. We have data showing you could have also CDW type of phenomenon, just like your question. Many things happen. Okay. In that case, okay, as your CDW turned on, okay, what happened was, as you go to the higher temperature, you have some charge over. As you go to lower and lower temperature, okay, you're naively saying, I would have add one more gap. Now we have that 79. CDW, okay, opened up a gap, go to superconducting state, by opened up a gap on top of that gap in the reconstructed Fermi surface. But in that case, then the condensation energy is the energy change at the Fermi surface pocket already reconstructed. what is different in this case is that as you enter the superconducting state, you see the CDW weakened. In other words, the CDW did a lot of damage by gapping out electrons. What is happening to a superconductor is actually suppress the CDW, in many ways restore some of the state, and using that state to build superconductivity. In one of the slides, I take pain to explain, if you look at high temperature, across the doping, the red and black spectrum, they look tremendously different. But when you look at the low temperature, the difference is much more subtle. In other words, superconductivity has already repaired some of the things. That aspect is much more stronger in this system than, say, a classical system like now the interstellar.
So I have a more general questions. I wonder, what is your viewpoint? This system has this new twisted bilayer system that offers these high superconductivity.
You mean bilayer
No,
nucleus?
twisted up. I mean twisted graphene, twisted bilayer.
I must say, I wouldn't say I have a strong opinion on twisted bilayer Cuprates. They're very different, so probably I wouldn't say I know about it. Yeah.
这个就是那个 electron phonon coupling. We say when it is too strong, the whole structure become unstable. Okay, so so is that true? Just maybe it has to do with this or not? Just in the superconducting state, sometimes I thought it become more anisotropic. Maybe that is electron phonon scattering channel just going in one direction. So is that a way to become anisotropic or one-dimensional in the superconducting state? Is the way to reduce the instability or strengthen the stability? What's your opinion?
It's a great question. I haven't thought about that. What I'm mostly thinking about is the phonon channels which need to be compatible with the D-wave superconductor. And you don't want to have a large momentum transfer. Because large momentum transfer means you're mixing positive and negative lobes of the wave function. That's bad. And so far there's plenty of good evidence that there's a small Q. And this, by the way, also come back to the idea of mirror. Remember he said that those are insulators, very poorly screened. You will find that if you look at the dielectric, in a situation of poorly screened, the phonon scattering will be forward and small Q.
So how could you give me the scale of the small Q? 0.1 angstrom universal.
So long as the Q are within this, I'm cool. But if you take a Q from here to here, that's not. Therefore, for example, the net, the B1G is about 25% of the zone. That's fine, actually, that's good. You don't want to mix this guy and this guy, but here,
Is it true in the iron selenide case for STL? Also only the small Q involved?
yes, we can. That is actually a lucky case we can even prove it's a small cube, because we see the dispersion and the phonon shifted dispersion looks identical. Okay. The reason in the iron selenium system, you see a dispersion look like this, and then you see a phonon replica like this. The only way, this looks identical, the only way this gives you this is your Q is 0, shifting. Otherwise, you'll be messed up.
Okay. So
this is the case we can prove that kind of makes sense when you have an interface. This vibration essentially from no Q.
Okay, I just have a question about the RPS. 30 years ago, I think Pigott has 30 milliamps on board. What about the current situation? What is the future possible?
I saw a most recent one. I mean, because we're working on high TC, 2 millivolts is good enough. But for people working on uranium, tellurium system, I saw beautiful results by UD10. It's about 0.2.
Yeah, so I'm interested about the phase fluctuation you mentioned in your talk. Yeah, and I remember because back in time when I was a student, I learned the phase fluctuation from Nernst effect. For example, people also see, well, the TC, and there's a debate whether it's due to amplitude fluctuation or is it due to the phase fluctuation. I wonder from RPS technique. So is any, you can say it's a,
yes.
it's a phase.
Remember I showed the singularity of a jump as a function of angle, and there's a very detailed calculation by Maxwell Franz and Andy Millis, what you should have expected the phase fluctuation and how data exactly.
I see. So it cannot be due to amplitude fluctuation.
Yes.
Okay.
Yes, one.
Okay, just a very light question. I mean, all these experimental evidence, they're just overwhelming. I mean, it's hard for someone like outside of the game to understand. So I just want to ask, I mean, Bardeen, must have faced the same problem because the low TC has been also, so in passage for so many years. So what are we waiting for? I mean, what character in Bardeen that is missing? Anderson is smart, but what are we waiting for? Is it a good recruitment like Bardeen got Cooper, or what do you mean by the star aligned? More specifically, what sort of person or what sort of characteristic do you think would require to actually break this and finally succeed to keep the secret?
I think it's a very good question with what is sort of is the one you will say sort of sealed. Maybe that's we can go back to the history of BCS. Remember, the BCS also took about half a century. The thing which is the reverse from BCS is that in the case of BCS, we understood the normal state better. So we have the protection of lambda Fermi liquid. And that instability of the lambda Fermi liquid, namely the Cooper instability. Remember that's Ian Cooper's work. That gives the superconductivity. Right? In the Cuprates, ironically, we actually understood superconducting state much better than the normal state. Right? That means we don't have the same framework of some normal state instability leads to that. We have a case for non-Fermi liquid. Okay. So it's that framework we didn't have. But without that, I think the phenomenology is very clear.
I think everyone got excited. It's the topic. So there's no ending in asking the question, but it's a very challenging topic. And I think this actually first time I see so many faculty here. Yes. So it's really people get exciting and they want to know more about, understand more current status. Let's thank Professor Shen for his. We prepare some dessert outside, so we can have some light moment to continue the discussion. Thank you.
不好意思，
照，
要合个照。
要照。